Assalamualaikum warahmatullahi wabarakatuh and good day. We meet again in the second lecture for the instrumentation and control system, basically about my topics. So I'm going to continue the one that we have discussed before. Before this, we on a little bit on measurement and the basic functional elements in a complete measurement device, or the basic instruments that need to have in a measurement system or measurement device. Now, as a continuation for that, I'm gonna go in depth on a few measurement concept, a few measurement knowledge that I believe is compulsory for everyone that want to design a measurement device or measurement systems, or engineers who in order for them to select an appropriate sensors for their applications. So I go to the next slide. Here's so what is variables? I've mentioned before, we do measurement because we want to establish a value. We want to give a value or quantity to the variables. For example, a moving car will generate displacement in terms of travel, or displacement in the engine. Also, a moving car will have velocity. We have accelerations variables. These are variables that related to the physical movement of this moving car. And the other example is a chemical reactor. A chemical reactor will generate temperatures, will create pressures, and also a composition, a chemical composition. So these are variables that related to the physical process. Other example, as stated here, force, torque, volume, mass, flow rate, level, density, viscosity, pH number, humidity, heat, current, voltage, and power, and many more of physical variables. And the variables, these variables, we classify into three types of variables, which is the first one is independent variables, which is a change in one variable will not affect the value of other variables. So this is independent variables. And then the second type of variables is the dependent variables, which is a variable that affected by the changes of one or more variables. And the last one is the extraneous variable. The extraneous variable cannot be controlled during the measurement process. Some says that extraneous variables is a noise, is some kind of noise. But sometimes extraneous variables can be something useful. So it depends on the application during the measurement. Okay, let's have a look on the example. So this is example of pressure calibration system. So we want to do a calibration. So we give some sort of movement or force to the chamber, and the chamber will give pressure. Will generate a pressure. So the input will be the load, and the output will be the pressure. So for this case, the independent variable is the piston displacement, because the movement of piston travel in X during the measurement will create a load. So load will give pressure to the will generate pressure at the end of the chamber. So the X displacement is the independent, because it doesn't depend on anything. We give we create the movement, the X value, and then as a result, okay, the dependent variables, which is pressure, the temperature. The temperature also involved. It also will affect it. Not only temperature, the volume of the chamber also decrease. So it will affect three things, which is volume, pressure, and temperature. So these variables is dependent variable. It depends on how much we push the x. And then there is an extraneous variables, which is can be the value of voltage in voltmeter, the power source, the outside temperature, the deformation of this the chamber, the cylinder. Actually, we don't know what these extraneous variables, because we didn't plan it. It maybe appear during the measurement. I have marked over there the noise effects due to the room temperature, line voltage variations, performance of the voltmeter, interference in the connecting wire between device. So this is the thing that happen during the measurement. This can be the extraneous variables. Maybe this is noise, maybe this is a good variables that we need to measure. But it's not the one that the first thing that important that we design during the measurement, which is the x as the independent variables, and the three variables that directly affected, which is pressure, volume, and temperature. Okay, what is parameters? Parameters, don't get confused with variables. Variables is quantity that varies, that can vary. That can, for example, velocity over the movement of the car. If we measure movement of the car, so the velocity will change. So we can say that the variables is a quantity that change over time or over space. And then what is parameter? Parameter is a functional group of variables. It is defined as a functional relationship between variables. For example, Reynolds number, where the value is determined from the values of a grouping variables. If you have time, go have a look. What is Reynolds number? It's actually a combination of a few variables. We calculate a few variables and then we put in the number equations, and we can get a Reynolds number. The Reynolds number, for those who study the fluid mechanics, they will know that Reynolds number will indicate the condition of turbulence during the flow. So it is now is a parameter. Another thing that we can as example for the parameter is a flow rate. A flow rate is a parameter. It's actually a combination of speed and the diameter of the fan or blade of the fan. So, and the equations which is down there. So let me show you. So this is the equation for a flow rate. So it's so this is actually a fan flow coefficient. So this is a flow coefficient. So if we move Q as the subject for this equation, we can get the equation that's related with N and the diameter. So that is the parameters. Okay, so the next term that very important in the measurement, which is the noise and interference. I have mentioned a few times about the noise, and I mentioned also about the interference. So what is noise and what is interference? What is different between noise and interference? Okay, a noise is a random variation of the value from the measured signal as a consequences of variations of the extraneous variables. I have explained before, the extraneous variables is something that we cannot control, or we didn't control during the measurement. If something is outside from measurement, but it's affected the measurement. And these variables create noise. So that is a noise. This actually, we can say it is unwanted signal. It is an unwanted signal that appear during the measurement. That is a noise. It creates data to scatter. It's scatter, more random. The noise cause the data to scatter. And then what is interference? Interference is it creates are deterministic trends. The trends that it is not predicted during the, I can say it's not predicted during the plan. Difficult to define what is interference. It's like, from the name itself, it's like something that interfere. Maybe one signal interfere with other signal, so interfere together, and it creates something else. So that's in a layman term, that is interference. The most important is it will impose undesirable deterministic trends on the measured value. So suppose that measured value goes straight line, the measured value will go uptrend linearly. So that's because of the existence of interference. Some signal, some extraneous signal, interfere with the measured signal and create the trends that's unpredicted prior to the testing. What is different between interference and noise? Noise always there, whether the measured data is there or not. We didn't measure anything, the noise is already there, because that is the noise. But for the interference, it's happened during the measurement. When we have measurement data, then we have interference. If there is a interference source around the area that we do measurement. All right. So this is actually the example of noise and interference. So this is actually the signal, true signal. So this is actually a noise. It always happen. If there is no signal, like for example, a straight line signal. So if a straight line signal, so this is noise. Noise will be like this. So let's say the signal is 0, so no signal. So noise will be there. It's always there. But in the existence of interference, only interference. So let me delete this one. It'll be like this. And this time there's no noise in the signal. So it will create some trend to the original signal. Okay. So let's say interference happen, the noise also happen. So what will happen is the signal will be like this. So this is the effect of interference and noise in the inside the signal. Okay. A measurement is actually an experiment. It's some sort of experiment. There's two things. The first thing, we want to calibrate the measurement device, so we need to do experiment. And when we do measurement, also is some sort of experiment. So everything is about the experiment. It's actually some sort of relative activity actually. All right. So for example, if we want to measure fuel consumption, so it involves the planning of experimentation. So we have to plan what kind of activity that we need in order for us to measure the fuel consumption. Not only the activity that we have to plan, we have to think about what is variables that involve during the experiment or during the measurement. We also need to find what is parameters that is important in the measurement, and also we need to find the source of extraneous variables, because noise and interference, we can see its effect after we see the measurement results. Then we can see the noise and interference. But before we can predict what is extraneous variables that might affect the measurement. How to set up the test plan? So first we look at the variables. We need to plan for distance, for fuel volume consumption. So these two variables. These two variables is the independent variables. So the dependent variables that we can think of is actually distance, movement to the car and give a distance, and also it will give the velocity or accelerations. There are also variables that may affect during the measurement. It's the movement of odometer. The movement of odometer, it also move. And also the way you fill the fuel. You fill it with high flow rates and low flow rates. Also, it will affect the fuel consumption. And other variables, maybe driving route, driving path, the driver, how the driver drive the car, the weather conditions, the road conditions. So these are might be the extraneous variables. Now, after we set up these the variables, then the identification of parameters and how the parameters can be controlled. Okay. And then we also need to design the technique for measurement, the equipment that we need to do measurement. We also need to think about how to do data reduction, because of course when we measure, we collect so many data. So which data is reliable, which data is true. Maybe we have a lot of data and the data will give a constant. So we have to plan how to reduce this data. It is more to the data presentation actually. For example, if we measure 1 day temperature in the step of let's say 30 minutes, it's a 1 day measurement. For step of 30 minutes, I think the data is not so many. But if we take data in the step of 1 second, each second we measure temperature for the whole day, give us a lot of data, and it might cause more difficulties. For example, maybe about storage problem. Maybe it will create a problem with the device. Device maybe hang is because too much data. We have to plan all these things before we do measurement. So the next term that is really important that we need to know about measurement, it is the replication and repetition. Repetition is repeated measurements during a single test. Okay. For example, you measure temperature 2 times, 3 times, 4 times, 5 times. So this is actually a repetition of a measurement at single test run. Meanwhile, the replication is actually an independent duplication. It's a duplication of a set of experiment. Okay, we do one time a single experiment here, and then we duplicate the same experiment at another place or another time. Maybe we do test today, we replicate the set, we duplicate the set to do a different experiment at different place. So what is calibration process? The calibration process is actually applying a known input into a measurement system for the purpose of observing the system output. Basically, the known value for the calibration is called a standard. It is important to do calibrations to check the instrument against the known standard. There is two kind of calibrations, which is the first is static calibrations and the second one is dynamic calibrations. For a static calibrations, the value do not vary with time and space. Only the magnitudes of the known input and the measured output are important in this case, for the case of static calibrations. The input for the calibrations, which is the known input, which is standard value, is a controlled independent variables, and the output value will be the dependent variable of calibration. So we apply a known input, and then we observe the output value, and then we plot the independent and the dependent variables in the calibration curve. So we see the relation between the independent and the dependent, and then we can establish the calibration curve. This calibration curve is very important for any measurement device or measurement system, in order for an engineer to understand their measurement device. What is the application or the use of the calibration curve? First is for determining the output display scale on the measurement system. The second one is to develop a functional relation between the input and output with the independent and the dependent variables. So this is example of calibration curve. This is actually the calibration curve which relates the y and x. So it can be any parameters, it can be any variables, but this is the relation. Either it's a quadratic a curve, or it's a linear curve. It depends on the result of measurement that we took during experimentation or during the measurement. So let us have a look here. So this is a k. The k value is the static sensitivity. Is how much the y correlate with the x. So it gives the value for k, which is the equation for static sensitivity. It is dy over dx. For the case of non-linear curve, which is quadratic like this, so at particular points, it have particular specific static sensitivity. For example, here at the point of x1, k for x1 is dy dx for x1 position. Alright, so same goes with this other position along the axis. So now we have a look on the dynamic calibrations. It's more to the dynamic signal, fast changing signal over the time and over the space. So this is a dynamic signal. Most of the time, the variables interest during the dynamic measurement, the dynamic calibration, is the time dependent. For example, in vibrations, the easiest example of dynamic calibrations is the calibration of vibrating equipments, vibrating sensor for vibrating equipments. For example, accelerometer, LVDT, and all this sensor is used to measure dynamic signal. Dynamic variables is time dependent, and then most important is the frequency content of the dynamic variables. It's not only a magnitude, also the frequency content of the dynamic signal is also important during the calibration. For the static calibrations, we establish a known input, which is a standard value. Here in the dynamic response, the dynamic calibration, the standard value or the standard input can be in the form of sinusoidal signal, or step signal, or a pulse. It must give a specific value to the signal. For example, we give a step signal with x amplitude, and the duration for the step signal is about 1 second, and then we see the response. Every time we do measurement, there's no measurement without error. There's no measurement without error. The only thing is, error is small or big. So we have to measure the error. The device that have less error is better. I think it's common sense. Low error, which means huge accuracy, more precise, and then less noise. So what is the error? So error is actually difference between measured value and the true value. So for the case of we don't know the true value, the average value during measurement can be the true value. Okay. So the equation for the error is as stated in the slide, which is the measured value minus the true value. In terms of percentage or relative accuracy, is the magnitude of the absolute value of E divided by reference value times 100. The reference value we will discuss after this. I will give you some example what is actually a reference value. We have two kind of error, which is random error, and then we have a systematic error. Random error is defined as a measure of random variation found during the repeated measurement. Systematic error is an error that remains constant on a repeated measurements. With the systematic error, it will create an offset or bias to the true value. If I want to relate with the previous discussion, the systematic error is related to the interference, and the random error is related to the noise. It's difficult to eliminate the noise, but to reduce a systematic error, there is a systematic way how to reduce the systematic error. We can reduce the effect of systematic error by having a random test. Random test, we apply the random input, and we see the effect of the random input and plot it in the graph. If we do calibration, we put it in the calibration curve. This the random input will ensure that the value is independent from the previous input. We give input 1 bar as an input for pressure, and then we give the next input is 2 bar. We don't know whether the 2 bar input that we give is related to the 1 bar that previous test. So in order for us to eliminate the effect of the previous measurement and the later measurement, we do random. We do maybe if the measurement is about input pressure, which 1 bar, 2 bar, 3 bar, 4 bar, so we do maybe 4 bar first, and then this 1 bar, and then 2 bar, and then 3 bar. So we do random, and then we look in the result. But this is only if systematic error appear during the measurement. The value that indicate how the system can be repeated or not is the precision. If the precision value is high, that means it's repeatable. The measurement is repeatable. High precision infers a low random error, okay, and is better repeatability. The precision is related to the repeatability. The accuracy, okay, the accuracy is related to the systematic error. If we can eliminate the systematic error, we can make our device, our measurement to become more accurate. This is figures that can explain the precision and the accuracy, and the random error and the effect of systematic error to the measurement, to our measurement. Data here, scattered data, okay, due to the random error, due to noise, it will give like a scattering effect, but in terms of average, it will average in one value here. But if the measurement also have systematic error, it will give some offset value from the true value. Okay. So this is similar to the discussion when we discussed about noise and interference. So basically, systematic error is due to the interference, and random error is due to the noise. I can explain with the use of this figure to explain more about accuracy and precision. So if you see this figure, it's precise, but it's not accurate. It have some sort of offset here, so it's some sort of systematic error to the measurement. For this one, of course, it's high accuracy and high precision, and for this one, there's a problem with the measurement. I think if we have result like this, that means our measurement device is totally cannot be used, because it's low accuracy, lot of offset, and then it's also very low repeatability or less precision. Before we go further details to the discussion of errors, we need to understand a few things. First is the range. What is the range? I'm referring here, the range is the lower and the upper limits of the measurement. Let's say the instrument is designed to work, for example, if I can use the example of thermocouple, it may have input range about 100 to 250 degrees C, whereby this input will give the output of 4 to 10 millivolt. So the input is always referred to the x-axis, which is to the independent variables, and the output is the dependent variables, which is the y-axis. So for this case, the input range is 100 to 250 degrees C, and the output range is 4 to 10 millivolt. And another example I can bring up is the pressure transducer, which is example, the input range is 0 to the 10,000 Pascal or 10 power of 4 Pascal is as an input, and the output is 4 to 20 milliamp. In other words, for the full scale input, the Ri or R for input, range for input, is x max minus x minimum, which is the range for the maximum of x, which is for this case input, the maximum, and input minimum. And then for the R range of output is from the y max to the y minimum. And the RO is we call full scale output, and the Ri is we call it full scale input. This is relevant to what we will discuss after this, which is the error. And the other thing is the resolution. What is resolution? So for this case, the resolution is referred to the smallest increment in the measured value that can be measured. For example, if I can bring up the regular ruler that you always use, the minimum or the smallest increment is 1 millimeter or 0.1 centimeter. Another example is the temperature, body temperature or thermometer that we always use for measuring our temperature. The smallest increment is 0.1 degrees C. So that is the resolution of the measurement device for the thermometer or the ruler. We have discussed about the error, about the random error and systematic error, and now we detail out what kind of errors that usually have during the measurement. We have hysteresis error, we have linearity error, we have sensitivity error, we have zero shift error, which is, I believe, zero shift error is related to the systematic error, and also we have repeatability error. For the zero shift and Repeatability error, it's more to the systematic error, but it can be detected by using statistical analysis. Okay. For the sensitivity error and hysteresis error and linearity error, we need to do a lot of experiment, repetition, to identify how much this error affect the system. First is hysteresis. A sequence test, a sequence measurement. Sometimes the hysteresis will occur during the in the results. Okay, so we have up value, down for the output, increase input, and then when we decrease the input, it will go like a curve down. So that is actually a measurement or a device that affected by hysteresis error. There is a way to reduce hysteresis, which is by doing tests in random, not in sequence. So we might reduce the hysteresis, but maybe not. But we have to try. So this is upscale. So this is downscale. So the difference between this value is the hysteresis error. This is y, this is an x. Alright, so for a normal test, it should be like this: y, x. It should go like this: go up and go down at the same rate. But if the system has hysteresis error, so it will have something like this. Alright, so the calculation is this. This is the calculation. Usually we write the hysteresis error in terms of percentage, or in terms of relative error relative to the reference value. So I've mentioned before this that when we calculate the errors, we must relate it with the reference value. So for this case, the reference value full scale output range. Some case we use full scale input range. Okay, so for the full scale output range, RO, because the O is we refer to the output, so full scale output. So where is the full scale output? For this case, this is the output. Because we know the input is X, the output is the dependent. The output is referred to the dependent, which is Y value. So this is output. So this is input. Sorry. So if full scale output, so this is a full scale output. So this is scale output. So this is a R naught. Okay, you put the value is there, and you find the maximum difference between upscale and downscale. Times 100, you get percentage. Sometimes we cannot avoid the sequence test. Some standard must require us to do sequence test. So if you need to do sequence test, and then make sure that you calculate the hysteresis error. The next error is the linearity error. If we have say y and x, so data will be like this. Data will be some scatter, something like that. So if you put average, it will give something like this straight line. It's not a straight line, but you can assume there's a straight line. So this is actually a linear graph. It should be linear. Okay. So data scattered around the linear line. So the difference between this point and the line linear is the error. So you can see here, there's a lot of data that is different. It's not on the line. So the difference between that dot to the line, we calculate in terms of y value. So for example, if I put this one, so this is the difference. Okay, so the difference between this point, so I say, let's say this is a y1 and this is a y linear. Okay, so the difference between y1 minus y linear is the error. This is the equation. Okay, so again, if you refer to the equation, this equation is just for all the data. If you want to find the relative percentage of error, so what we do is we find the maximum difference from the data and the linear line, and then you divide with RO. Remember, what is RO? Is the full scale output range. So for this case, from here to here, so this is the R output. Okay, so you can calculate the percentage of linearity error. If you recall, the linearity and the hysteresis error, it is the relative error compared to the scale, to the output scale. Okay, if the measurement have a very large scale of measurement, okay, very large scale, and then the difference between the error, okay, is small, so that means the error will be small. So but with the same difference, randomization inside the scale, but the range of scale is small, so that will increase the relative error. So how to calculate the repeatability error? This is the equation. You calculate Sx, which is the standard deviation. You can calculate the standard deviation. You times 2 and you divide by, again, this is a full scale output, and then times by 100. So we will have a look on the standard deviation later on at the final topic in this in the discussion of measurement. After we discuss on the errors, a few important errors for the measurement, now we have to look on the uncertainties. So what is uncertainties? The uncertainties refers to the estimate of the effect of the errors on the results of a measurement. The uncertainty that we set or we assign to the instrument is actually the effect of first random error, and also the second is the systematic error. If we have a lot of error, we already analyze errors for the instrument, and when we want to combine all these things, we want to summarize in terms of one uncertainty value. So this is the equation that we use. UC is equal to the power of each of the uncertainties that reflect to the error, and then we plus together all these uncertainties, and then we square root, and then we can get the total uncertainty of the instrument. Alright, so when we develop an instrument, we must make sure that our instrument follow standard, and also the output of the instrument also need to follow the standard, or either the standard of the dimensions and also the standard of the units. For me, the most important is the standard for units, because we have two main units that we use, which is the imperial unit and also the SI unit or metric unit. So this is, for example, for length, the SI unit we use meter, For the imperial unit, use the inch. And then we have mass, also have a different usage of units, but they're giving same unit, which is same dimension. They are measuring the same dimension, which is the mass and length, but we give a different units. This units is not the same. We need to have a conversion value. We need basically we need to make sure that our measurement device, either we can give both values. Nowadays, if in digital instrument, we can provide both values in SI units and also in imperials. But for the case of we use analog instrument for measurement. Either we show one unit, and then we provide the conversion for the measurement. We also can put in instruction to make sure that people understand that the output of the measurement is in what unit. If we use SI unit, we have to make sure that the user understand that we use SI unit. All right, so not only in terms of units, we also need to standardize in terms of the dimension. We also need to consistent in terms of derived unit, because a derived unit, for example, to indicate the units for energy, some use joule and the others might using the Newton meter, although they indicate the same quantity, which is the energy. So we need to make sure that we inform the user the kind of output that will be given by our instrumentation. In the existence of random error in our measurement, it is important for us to analyze the data in terms of statistical analysis. But before we go to the statistical analysis, we have to understand a few things. We have to understand the difference between sample and data. When I talk about sample, it refers to a set of data in a repeated measurement. The data itself is one reading or one measurement. So there's a difference between sample and data. In one sample, there is a lot of data. The data is come from a repeated measurement. Of course, this is the same condition in the unique same condition, and then we took a lot of measurement, which is one measurement referred to one data, and all this data is referred to one sample. So when I say sample A, there is a set of data. Sample B, there is another set of data. So that is what I mean by a sample and a data. And data referring to the physical variables that we measure, and that variables is we call measured variable or the measurand. A data refer to the one measurand, and a set of data we call it one sample. Okay, the data that we took during our measurement or during a calibration of an instrument, basically it will distributed in normal distribution. When we talk about distribution of data, there is a few ways that data can be distributed, which is we have a normal distribution, we have log normal, we have Poisson distribution, we have Weibull, this, and we have binomial distribution. And basically normal distribution is basically for the data that infected by random error. But in mathematics, we also use normal distribution for random data, the data that not being influenced with by anything, just a random sample, random data. So it's basically will be distributed in normal distribution, or basically we call bell curve. Right. When they form a general shape of normal distribution, which is the bell curve. So this is the equation that form that bell curve, and then in the equation, if you have a look on the right side of the equation, it have the two informations from the statistical information, which is the mean value x prime and the variance. When we talk about normal distribution and a random data, we can say that the data will appear in, we can summarize the data in some interval. Later on we will see the example, but first we want to establish these things so that we have more understanding of this one. Let's say we have x, the measurement of x, and then we took about, let's say, 1000 measurement. So we can say that x will appear in interval of x prime, which is the mean value, plus minus the interval, which is for this case it is z1 times variance. So if I can use this bell curve stated here, so that here is the x prime, so let's say this side is the plus z1 times variance, and this side is negative z1 time variance. Alright, so the how much is moved to positive side and how much is moved to the negative side is depend to the value of z here. So the bigger the size, the numbers of z1, it will cover most of the data in bell curve. So the smaller value of z, it will cover only one small area of the curve. All right. So what is z? Z1, a number that we can get from the value of the statistical information from the data, which is here. Mathematicians have already established a table. This is the table that I'm talking about. This is the z value here, and this is the probability of the z value, or it is pz. So whatever value of z, say z1, it will go from the table, it will tell us what is the value of pz1. Alright, for example, if I say I want to find z1, let's say I took a very small value of z, so let's say 0.01, so it will map to pz1 is here, this one, so 0.04. So that is the value for pz1. So it will move about 0.04 to the left side and right, left side and right side. So 0.04 is only just small. If we talk about left and right, so which means it have 0.08, because 0.04 to the right side and 0.04 to the left side. So total we have 0.08, or 8% of the area in the bell curve. So it's very little. So let's say we have a larger value for z1. We have z. Let's say I put a z2. Let's say z2, I put a larger value. Maybe I take about 1.5, say 56. So 1.56. What is the value? So the value for y56 is here. So it's about here. So p z1 is about 0.44. Sorry, let me write it again. 0.4406. So if I can say in like two sides, so one side it goes 0.4406. So for two side, let's say for two side, oh sorry, I need to fix this one. It's not Z1 here, it's Z2. So because this is Z2 here, so 2Z2, I said 2 because it's two side, left and right. So it's about 0.8812. So it covers about 88% of the area. Let us have a look on the example. Let's say we have Z1 equal to 1, Z2 equal to 2, Z3 equal to 3. So find the probability of the data to appear when we say the interval is Z1, Z2 equal to 2 and Z3 equal to 3. Let me fix this statement first. What I mean by here is actually find x prime z, actually they're missing the z here. Okay, so please fix it in your notes. So z1 prime, so this is actually the actual statement. Sorry, I'm missing the, let me fix this one. Okay, the same that we discussed just now in the previous discussions, previous slides. So that you find Z1, Z2 and Z3. So its value for BZ is 0.313, 0.4772 and 0.49865. For Z equal to 1, Z equal to 2 and Z equal to 3. So the result is Z equal to 1 is 68.26% and Z equal to 2 is 95% coverage, and Z equal to 3 is 99.74%. So in the figure we can look like this. So you can see in the figure, so the larger value of Z will give the larger area of the measurement to appear in the range, in the interval. Alright, so now we have a look on the finite statistics. The one that I mentioned just now is a general information of the statistics, which is what we call what I can say it is actually a the set of data that covers all data, or we can say it infinite statistics. We call this, it describe a true behavior of the data because we compile or we summarize all the data in a measurement. Let's say we have 1,000 measurement, 1 million measurement, and we have 1 million data in one sample. So if we summarized all the information using statistical information, for example mean, variance and standard deviation. So the information will give the true behavior of the data because we take all the data. But for the finite statistics, we only pick just a few sample. For example, let's say first 20 sample, or the mid 20 sample, or the last 20 sample. So we only take just a finite size of sample. We do this maybe because of we don't want to measure all data. Maybe we don't have time to measure all data. Let's say if we have in a university we have 1,000 students. So if you want to have a true results when we study the behavior of all students in university, let's say 1000 students, so we need to interview each one of the students. So the result will give the true behavior of all the students that we interview. But if we don't have time, we only pick a few of the students, okay, and then ask or interview them about whatever thing that we want to interview. Maybe if you want to study the students' diet, for example. So we don't want to take all the data. We only take a few data. But hopefully that data, that small data, can represent the behavior of the whole set. So, but it depends on the result. It may have a probability of having a true behavior, but it also may have a probability of not having the true behavior. I will discuss about this later on, because we have some calculations, statistical calculation, to indicate the probability of the value will show the true behavior or not for the data, for the finite statistics. Right, so for the finite statistics, the standard deviation and the mean calculation and the variance calculation is as stated here. So this is for the mean value. If you want to calculate for mean value, n in this equation is referred to the number of data in the sample, and x is the data itself, and then the s, this is a variance for the finite data. The variance we say in s x power of 2. For the infinite, we use this symbol. Alright, so and then this is for the standard deviations. Alright, so if for infinite data, the data will look like this. So say x prime plus minus z1 times variance. So this is indicate the interval of the data. But for the finite statistics, x will appear in the interval of, we say, because with finite data, the symbol for mean value is x bar. X prime is referred to the true behavior of the data, which is for the infinite data, infinite statistics. So plus minus. Now we no longer have t, z1. We use t, v, and p times the standard deviation. So this is indicate for a finite size of data. So x will appear in the range of x bar plus minus the interval, which is tvp times the standard deviation. So what is tvp? So we get the value for tvp from a table, in the student t distribution table. But another question is, what is v and what is p? So v is actually a degree of freedom, which is equal to n number of data in one sample minus 1. So this value for v, and p is the probability value. For example, p for t 95 or t 99 or t 50. We need to look at the table so that we can understand what is this. Alright, so before we go to the table, I've mentioned before this that for a finite data, the data we only take just a few sample from the whole data. So it might have a different, the mean value, it might not represent the true value. Remember, the true value is true if we take the data from all data, from all the sample. Alright, so and then if you take just a finite size, so the x bar or the mean value for a finite size, it may be different from the true mean. How to indicate how much it deviates, how much it different from the mean value of finite data to the true mean value. So how much is different? We can use this equation. So this is actually the true value, and then this is the mean value. So this is interval. Still we use TVP, which is the we get from the table, but this one is not standard deviation, but it is a S x bar equal to actually a standard deviation over the square root of n. So from this equation, we can find the interval of how much the true value is different from the mean value of the final sample or finite size, data size. Alright, so this is actually the table. V is on the most left side of the table is the V degree of freedom. Remember, it is equal to n minus 1, and then so the another side we have T50, T90, T95 and T99. So this is actually a same with the P. So it's actually a P, the probability. So remember, we have PZ1 before. Okay, this for infinite data. For this one, we have P for let's say T50 or P for T90 and so on. Okay, so I might write this one so that you might get the idea. So P with T99. So we have a lot of P here. So to get the value for T VP, we need to know the V and we need to know the T. Then we can find the TVP. Alright, so we go to example so that we can understand more on how to use this equation or this statistical analysis. So let's say we have 20 sample. We collect 20 sample from actually a infinite data, which is only take 20 sample, and the value is given there. So from the rough looking, so I can say that we have a maximum X number is about 1.34, I think. Correct me if I'm wrong. And then for the X minimum, we have 0.68, I think. Again, correct me if I'm wrong. But this is, so from this data, it is 100% data will appear in the range of 0.68 to 1. Sorry, let me correct this one. 1.34. So in this range, 100% of data will appear in this interval. So the question is, calculate or compute the sample statistics for this data set. And then the second question is to indicate or find the interval where 95% of the data will be appear in the interval. And also number 3, estimate the true value of the measurement at 95% probability based on this data set. C, I will explain later on, but we focus on A and B first. So we know that data is 20 data, and then the data is normal distribution and finite data size, which is 20. The n is 20, and then of course with the n 20, the v is n minus 1, which is 19, and the mean value, we just use the equation, and then we can get this one for mean value, and then the standard deviation by using the equation, you get 0.16. Then with that, we go to the table. Remember, it is about 95%, so T for 95, and then degree of freedom of 19, we found that it's appear about 2.093 away, plus minus, from the center value of the bell curve. So it's quite large. 2 point something is quite large. Again, it is 95%, so it must be very large area on the bell curve. And if we use the equation that I have stated earlier, so the x will appear in x bar, which is we calculated using the equation, plus minus, so the TVP times the standard deviation, so it will be like this. So okay, so 95% of the data will appear in the range of given here, so it's between 0.96 to 1T5. So 95% will appear in this range. Alright, so the question is for number C. I want to explain a bit on that. So like as mentioned just now, this is only a sample of finite size, so the mean value is not a true value. It must have some sort of different from the true value. So we want to find the interval, how big the interval. For 95% confidence, the data will have different from the true value. So we find the x S bar, standard deviation, the deviation of mean value from the true value, which is standard deviation over divide by square of n, which is the value is 0.04, and then put in the equation. So you find that it's actually 95% probability that the mean value is actually offset to the true mean value. It's very small, just only 0.08 different, plus minus, from the mean value. So it's about like 0.94 to 0.10. So it's just a small interval. Alright, so that's I finished my discussion on this statistical analysis topic about the data, about our measurement. So with the end of this discussion, so I also end the topic for the fundamental of measurement. So hopefully we can we can meet again in the next lecture. So thank you very much for listening to the lecture, a quite long lecture for the fundamental of measurement. So see you later. Thank you very much. Assalamualaikum.